One day, everything we know will cease to exist. Today, the universe around us is vast, radiant, and incredibly dynamic. Stars are born and die. Planets emerge and vanish. Black holes relentlessly devour matter. But behind this ordered chaos lies an expiration date. Surprisingly, it is written in the heart of particles so small we can hardly imagine. You are about to discover the particle that could decide the fate of the entire universe. But first, let us go back in time. At the end of the 19th century, humanity was still trying to grasp the structure of matter. Back then, atoms were believed to be the smallest parts of the universe, indivisible and solid, like tiny spheres. But that was about to change. It was during this period that J.J. Thomson revealed the existence of the electron. This groundbreaking discovery shattered the long-held belief in the atom's indivisibility. The atom was no longer a fundamental, unchangeable unit. Soon after, physicist Ernest Rutherford conducted a decisive experiment. He shot alpha particles at gas atoms, and the impossible happened. The nucleus, once seen as solid, split apart. This unexpected result provided undeniable proof that there was something even smaller within the atom. It was a moment that redefined our understanding of matter. The proton was born. But Rutherford did not know that he had just uncovered the particle that might decide when the universe will end. Today we know that protons are everywhere. You are made of atoms, and atoms contain protons. They are the fundamental building blocks of all ordinary matter. Yet even protons are made of something even smaller, quarks. These, as far as we know, are the most fundamental building blocks of reality. They are the ultimate constituents of the universe's visible matter. But how does this work? To understand, we need to talk about an essential concept: radioactive decay. Decay happens when unstable particles lose part of themselves, transforming into others. This process is a fundamental aspect of the subatomic world. That is how very large nuclei, like uranium, break apart, emitting alpha particles. This transformation is a natural consequence of particles seeking a more stable state. It is a constant, silent dance of creation and destruction at the quantum level. And here is the most intriguing part. Even protons and neutrons can decay. Inside atomic nuclei, there is instability, a constant push and pull of forces. But the proton is special. According to the standard model of physics, the proton is immortal. This model, our most successful theory of particle physics, describes the fundamental forces and particles that make up the universe. Properties like electric charge, energy, and baryon number are conserved. This conservation, in theory, prevents the proton from disintegrating. It is considered a stable, unchanging entity within the framework of our current understanding. But what if it can decay? In 1967, physicist Andrei Sakharov raised this possibility. What if the proton were unstable too, like so many other particles? This was a radical idea, challenging a cornerstone of physics. Proton decay would be a sign that there is something beyond the standard model. Perhaps it is a clue to a grander theory, a more complete understanding of the universe's fundamental laws. Grand unified theories predict this. These ambitious theories attempt to unify the fundamental forces of nature, and many of them suggest that protons are not truly stable. If confirmed, it would change everything we know about the universe. But to this day, no experiment has detected this decay. Billions of protons have been observed for decades in massive underground detectors, yet none have been seen to spontaneously break apart. This means that, if it happens, it takes longer than 1034 years. This is an unimaginably vast timescale, far exceeding the current age of the universe. Now imagine when the universe reaches that age. White dwarfs, the remnants of stars like our sun, will begin to disintegrate. These dense, cooling stellar cores will slowly shed their matter. Each decaying proton will release high-energy particles. But the glow will be faint, comparable to a solitary light bulb in an infinite void. It will be a final, almost imperceptible flicker of light in the cosmic darkness. And when that glow fades, all that remains will be a cold, dark sphere of iron. The once vibrant star will have completely vanished, leaving behind only a silent, inert husk. The same will happen to neutron stars. These incredibly compact, dense objects formed from the most extreme matter in the universe will also slowly vanish. Their immense gravitational fields will not be enough to prevent the eventual decay of their constituent protons. The universe will then be a void. Only black holes will remain, slowly evaporating through Hawking radiation. Even these cosmic behemoths, the ultimate devourers of matter, will eventually dissipate into nothingness. And if protons are eternal? In that case, the universe will not escape another fate. Stars will still die, galaxies will dissolve, and only faded remnants will remain. Cold white dwarfs, energy-depleted neutron stars, and planets drifting in the dark will populate the cosmos. Matter will persist, but in a silent, static universe. There will be no new stars, no new light, just a vast, cold expanse of inert matter. Even so, there is something that will continue. The iron spheres, stellar remnants, will slowly increase in density. Over trillions upon trillions of years, with nothing to stop them, they will collapse into black holes. This process, driven by the relentless pull of gravity, will be incredibly slow, but inevitable. This collapse will take around 1070 years. This number is so astronomically large it defies comprehension, representing a timescale far beyond anything we can truly grasp. And when even black holes have evaporated, the universe will hold only radiation. The last vestiges of matter and energy will have dispersed into a uniform cold bath of photons. The cosmos will enter its thermal death, nothing else will happen. Absolute silence, an irreversible balance. Perhaps the universe will not end with a bang, but rather with a whisper. Perhaps we may never witness the decay of a proton, or perhaps it may never happen. But the very possibility changes how we see time, existence, and our place in this infinity. Because in physics, we do not always have all the answers, but we always find the right questions. Like and subscribe to the channel to support our work and continue having more videos like this. Thank you, and see you soon.